Welcome to week 1 of Geology 204 Earth and Life History for the spring 21 semester. For all of the logistics of the course, what our schedule is going to be, how you're going to be tested, all of that, I want you to go and read the syllabus. The syllabus is in the week 1 module of the course. It answers everything. Of course, every professor says that. And it's true, but if you just at least give it a look, you'll do much better through these early weeks of the course. But don't worry, I will continually be reminding you of deadlines and things like that. For the rest of week 1, this little shortened week we have after Martin Luther King Jr. Day, I'm not going to present any new material. I believe in starting slow. So your assignment for week 1 is reading that syllabus, understanding what's going on, and then just listening to me as I describe quickly here the 4 major themes of the course. If you look at the title, Earth and Life History, one of the things that you should be able to get from that is that it's going to include both geology, that's the earth side, and biology, that's the life side. Collectively, those two together form the science of paleontology, and that's what I am, Rex Hanger, a paleontologist. I'll give you a little video explaining a little bit more about me probably later this week or maybe early next week. But for now, just realize I'm a paleontologist. I study ancient life forms throughout Earth's long history, and that's what we're going to be covering in here. And there's 4 major themes to the course, which parallel the 4 major themes of how this science is done. And so the first one is, simply put, the Earth is dynamic. It's not stable. If you look at that bottom map there, that's the world that you've known since you were a little kid. Remember, you had to memorize the continents, the oceans, all that good stuff. Well, that's not fixed. We take it for granted that the map is the map is the map, but if you go farther and farther back in time, none of those continents were in the same places, and therefore the oceans weren't in the same places or didn't even exist. And in fact, look at the way this is stepped off here. At the bottom, it's today. That's the map you should recognize. But then 65 million years ago, 135 million years ago, if you go back 200 million years ago, you basically have 1 continent and 1 ocean. So the Earth is dynamic, it's not stable, it's always changing, and that's the whole subject of plate tectonics. So we'll do a section on plate tectonics for you. One of the things to think about here is that means that we here in Wisconsin, which we now are in a frigid winter wasteland covered in snow and ice, haven't always been that way. In fact, the bedrock below our feet here in southeastern Wisconsin tell us that this part of the world was once a tropical paradise underneath the ocean and even south of the equator. So this map right here that you're looking at is what we call a paleogeographic map. You can see the outline of the Great Lakes. They didn't exist back then. But they're put there just so you can kind of orient yourself. So here's Lake Michigan, and where I have the cursor now is where we are. And that red line is the ancient equator, which marks the separation between the northern hemisphere and the southern hemisphere. And so you see, not only were we in the tropics, we were on the other side of the globe, in the southern hemisphere. The second major theme of this course is that the Earth is ancient. I know you think of some things as being old, like, oh, your grandfather is old, his car is even older, etc., etc. But that's nothing in a geologic sense. For geology, the Earth is measured in millions and billions of years ago. If you look at that picture there, there's these dinosaurs having a very bad day about 65 million years ago when an asteroid hit the Earth and they went extinct. And we'll talk about that. We'll talk about big events like that, but we'll also talk about how we get big numbers like that. How do we know that the Earth is millions of years old? How do we know that it is called by such terms as the Cretaceous, the Jurassic, the Pleistocene? It's all part of geology and geologic time. And geologic time can be very, very old. So it's not always just sexy things like those dinosaurs. What you're looking at here is just a pile of algae, an algal mat, but this is about 3.5 billion years old. We call this thing a stromatolite, this sort of mat of algae, and the time period that we're talking about is what we call the Archean. You're going to learn a bunch of these numbers, you're going to learn a bunch of these events, and you're going to learn a bunch of these names as well as we sort of go through the calendar of life through time. The third major theme about the course is that not only is the Earth dynamic and we have all those millions of years, but life on Earth is also dynamic. Organisms are always changing. I know that you can go out into your front yard and an oak tree is an oak tree is an oak tree. And you can look at photographs from 150 years ago and oak trees are still oak trees. Blue jays are still blue jays. Rattlesnakes are still rattlesnakes. But remember, we have hundreds of millions to billions of years of time. And the slowest, most infinitesimally small changes in organisms multiplied by those long time periods can give us everything. And so what you're looking at there is the beautiful beast Dimetrodon. We say that this lived in the Permian period about 285 million years ago. And they certainly don't exist today, but their descendants do. And I know that a lot of you look at this thing here and you say, ooh, that's a dinosaur. That was in my little kit of toys from when I was a little squirt. It's a dinosaur. Well, it's not a dinosaur. We have good evidence that this organism is actually more closely related to you and I. It is part of an evolutionary lineage, the left side of this diagram here, that ultimately becomes mammals. We get these lizardoid type creatures that get progressively more and more efficient at regulating body temperatures, evolving hair, and ultimately becoming mammals. You are more closely related to Dimetrodon than any dinosaur was, because dinosaurs are a completely different evolutionary lineage that evolves from this same ancient lizardoid type ancestor. Interesting to think about. And then the last theme of the course is that sedimentary rocks record this history. If you talk about the history of anything else, if you think about the word history, you think, well, you know, history of countries, history of presidents, histories of wars, all the things on the History Channel. How do you do history from things that are so old? There certainly wasn't anybody around to write it down or record it. Well, it is recorded in rocks on planet Earth, and in specific mention, we need to talk about sedimentary rocks. And so you're looking here at a Google Earth satellite image of the Whitewater Limestone Quarry. The prominent sort of highway at the bottom going from left to right is Highway 12. So if you're going towards the right, that's the road you take if you're on your way to Elkhorn, Lake Geneva, points in northern Illinois. And the big hole that you see here is that quarry that you notice as you're driving on the highway there. If we sort of tilt the view, give it a three-dimensional view, one of the things you see here is that they are blasting and quarrying out a bunch of rock. They use it for construction purposes. But why it's of interest to me and to geologists is that the rocks immediately say to us, once we look at the fossils, that they are what we call the Ordovician period, that these rocks are between 485 to 444 million years old, and they're what we call the Galena Formation and the Platteville Formation. So yes, a rock is a rock is a rock, but if you're trained in a geologic sense, you can tell the age of the rock, the environment of the rock, and all of that. And that actually becomes useful for getting resources. Now here the resources are just gravel for road making and making limestone, cement, that kind of stuff. But think about all the other things that come from the earth: oil, gas, gold, silver, precious metals, base metals, all of that. to truly understand how to get those things out efficiently and economically, we have to understand this whole subject of earth and life through time. So if we go to this quarry again, the same theme, sedimentary rocks record this long history. Here are a couple former students of mine, and they are quarrying, prying out and busting up rocks from the wall here. And one of the things that we can see is that these beds of limestone are very prominent here, and limestone itself is a rock such that given its chemical formula, it can only be made in tropical oceans. So this verifies the other evidence that I showed earlier, that we were a tropical paradise under the ocean water in this warm Florida Keys type environment. And what do we find there? Again, more evidence to suggest that there is, this was ocean life, ancient ocean life. The metal object in the top of the picture there is the tip of my geologic hammer, but this long thing that kind of goes over here next to it, that is from an ocean creature that we call a crinoid. Today they live in the oceans. They have only ever lived in the oceans, so finding a fossil of it again verifies that these are ocean type rocks. This beast right here between my fingers, it looks like a beehive or something like that, and it's actually called a honeycomb coral. It's a coral head. And again, as many of you know, corals are found in the oceans, not on land. So again, we're just going a few miles from campus here, not even a few miles, just a couple miles, and we're getting evidence of ancient oceans that I and my students can collect here. These little shelly bits here, you might say, oh, those are little clams. Well, they're like clams. They're brachiopods. And again, they only have ever lived in the bottoms of oceans. They still do today. Again, evidence of oceans in this area. And then this, of course, is a snail. You can see the little spiral shape of this Lophospira here. All of these things are bits of evidence that confirm this ocean environment that we used to have here. And then finally, trilobites. So next to my finger here, you can barely see it. It's not a good one, but it's clearly evidence of a trilobite, which incidentally is our Wisconsin state fossil. So here's a patch that, you know, kids can get from our Wisconsin state parks if they could do a whole bunch of little exercises and earn the thing. And it has this picture of this beautiful Flexicolemene, which is our state fossil. So even our legislators, maybe they don't know so much about geology, but they recognize the importance of these things this way. And this trilobite, well, its ancestor to all kinds of things that you know of as seafood. I just goofily took this picture from Red Lobster, where you've got your shrimp and lobsters and crabs, but those things in turn are also related to ants, bees, beetles, moths, butterflies, all of those things. So again, to go back, you need to remember the four major themes of this course. The earth is dynamic, and it's very ancient. The life on earth is also dynamic, and how we know this, the record of all of this, is in these sedimentary rocks. That's what we'll be covering the rest of this semester. We'll start in earnest on week 2. See you then.